Okay, so you're listening because you're curious about state space models, SSMs. You want to know if they really are better at handling information over time, like, understanding a conversation or predicting stock prices.
We're going to dive deep into a research paper that challenges some of the assumptions about these models.
Yeah, and that paper is called The Illusion of State in State Space Models.
And it suggests that these models, despite their name, might not be as good at tracking state as we thought.
Okay, so before we get into the illusion part, remind me, what does state even mean in this context? It sounds kind of mysterious.
Yeah, it's actually a pretty intuitive concept. Think about reading a book.
Okay.
To understand what's happening, you need to remember who the characters are, their relationships, what's happened in the plot so far, all that context. That's state.
Okay, so like all the information that builds up over time and it helps us make sense of what's happening in the present. Got it.
Right.
So AI models need to be able to track state to really understand complex dynamic situations.
Yeah.
So where do these SSMs come in? What makes them different from, say, those transformer models everyone was talking about a while back?
So SSMs were designed to be more efficient and potentially more powerful than transformers.
Okay.
Particularly when it comes to tracking this state information. They're built around this idea of recurrence, which means they process information step by step, kind of like how we humans do it.
So they're more like the human brain, processing information sequentially rather than in those big parallel chunks like transformers.
That's the idea, yes. And because of this recurrent design, there was a lot of hope that SSMs would be much better at handling tasks that rely heavily on understanding the flow of information over time.
But then this paper comes along and says it's all an illusion. That's a pretty bold statement.
It is, yeah. And to understand why they make that claim, we need to get a little bit technical. The paper delves into this concept called circuit complexity, which basically refers to the types of computations a model can perform. And what they found is that SSMs, just like transformers, fall into a category called TC0, which has limitations when it comes to representing complex state changes.
Key C0 sounds like something out of Star Wars. Break that down for me. What does that actually mean for how these models work?
Imagine you have a team working on a project. If everyone can work on their tasks simultaneously, that's what we call high parallelism.
No.
It's efficient, but it only works if the tasks are independent of each other.
Right.
But many real-world problems, especially those involving state, require a more sequential approach. One task needs to be completed before the next one can begin.
So it's like building a house. You can't put up the walls before you lay the foundation, right?
Exactly. And what the paper argues is that SSMs, like transformers, are fundamentally limited to those highly parallel computations. They struggle when things get too sequential, too intertwined.
So even though they're designed to be more like the human brain, processing things step by step, they still hit a wall when the complexity ramps up.
That seems to be the case. They can handle simple state changes, but when the relationships between different pieces of information become more complex, their performance suffers.
And they illustrate this with a really clever example, right? Something to do with playing cards.
Yes. They use the example of shuffling a deck of cards. To track where each card ends up after a series of shuffles, you need to remember the exact order in which each shuffle happened.
Right.
It's a very sequential process.
Right.
And the paper demonstrates that SSMs, just like transformers, struggle with this task.
Okay, so shuffling cards, that's something everyone can understand. But what about more real-world scenarios? Like, how does this limitation play out in tasks that AI is actually being used for?
Well, they explore that too, looking at things like following the moves in a chess game, understanding computer code, and even tracking characters in a story. All these tasks require that ability to keep track of complex sequential state changes.
So what you're saying is that even those cutting-edge SSMs with the fancy names, they might not be as good at these tasks as we thought.
That's the implication. And they didn't just theorize about it, they put it to the test.
All right, spill the tea. What happened when they actually tested these models?
So they designed this experiment to see how well these models could learn to track permutations, just like our card shuffling example. They compared a couple of popular SSMs, S4 and Mamba, against a transformer, and just for good measure, a simple RNN.
A classic RNN. Those are like the dinosaurs of the AI world, right?
Right, but sometimes the classics still hold up. And in this case, the RNN, even with just a single layer, absolutely crushed it. It learned those permutations with ease.
Wow.
S4 and Mamba showed some potential, but they needed many more layers to even come close to the RNN's performance.
Wow, so even in a task designed to show off their strengths, the SSMs fell short of the good old-fashioned RNN. That's quite a reality check.
It is, and it really drives home the point that the state in these state space models might be a bit of an illusion.
Yeah.
They can handle simple state changes, but when things get complex, they stumble.
But wait, I have to imagine the researchers didn't just leave us on a cliffhanger of despair. There's got to be some glimmer of hope, right? Some way to overcome these limitations.
There is. While the paper highlights the current limitations, it also proposes a potential solution, a tweak to the design of SSMs that could make a world of difference.
Okay, I'm all ears. Give me that optimistic AI outlook.
They suggest making something called the transition matrix dependent on the input data.
Transition matrix. Remind me what that is again? We talked about it earlier.
Think of it as the rule book that governs how the model updates its memory as it processes each new piece of information. In current SSMs, this rulebook is fixed. It's always the same no matter what the input is.
Okay.
And that contributes to their limitations. But what if we made that rulebook flexible, allowed it to adapt based on the input?
So it's like giving the model the ability to change its strategy depending on the situation. Kind of like how a chess player adapts their moves based on their opponent's actions.
Exactly. And this seemingly small modification could have a huge impact on how effectively SSMs handle complex state changes.
That's pretty mind-blowing. But is there any evidence that this actually works? Or is it just theoretical?
Well, they put it to the test, of course. They implemented an SSM with this input-dependent transition matrix, and you guessed it, tested it on the permutation task.
Wow.
And the results were incredibly promising. This modified SSM with just a single layer was able to track the permutations just as efficiently as the RNN.
So this tweak could be the key to unlocking the true potential of SSMs. It's like giving them a superpower upgrade.
It certainly seems that way. Of course, more research is needed to explore the full implications of this modification and see how it performs on a wider range of tasks.
Right. We're still in the early stages of understanding these models and what they're capable of. But this paper provides some really crucial insights into both their limitations and their potential. And it reminds us that even with all the hype around AI, it's important to be critical, to look under the hood and understand how these systems actually work.
Absolutely. It's about developing informed skepticism, not just blindly accepting claims of superhuman AI abilities.
So for you, our listener, what does this all mean? Why should you care about these seemingly abstract findings about circuit complexity and state tracking?
It's about more than just knowing facts. It's about developing critical thinking about this rapidly evolving world of AI. You now have a deeper understanding of the current limitations of popular AI models, limitations that even the experts might not fully acknowledge.
It really makes you wonder if these state space models are hitting these fundamental limitations. Where do we go from here? Do we keep trying to refine them, or is it time to start looking for entirely new approaches?
Yeah, that's the million-dollar question, isn't it? This research really throws down the gauntlet for the AI community. It's like we've hit a fork in the road. One path leads to optimization, tweaking those transition matrices, finding clever ways to work around those limitations within the existing SSM framework. The other path leads to more radical innovation, exploring entirely new architectures, models that are fundamentally designed to overcome those limitations and truly master state tracking.
It's exciting to think about what those new architectures might look like. Will they be inspired by the human brain, drawing on insights from neuroscience, or will it be something completely different, something we haven't even imagined yet?
It's hard to say, and that's what makes this feel so captivating. We're really just scratching the surface of what's possible with AI. And the beauty of it is that the journey is just as important as the destination. Every experiment, every breakthrough, every stumble along the way teaches us something new about the nature of intelligence itself.
And that's where you, our listener, come in. You've now got this deeper understanding of the complexities of state tracking, the limitations of current models, and the potential for future breakthroughs. You're equipped to follow this journey with a more critical and informed eye.
Don't be afraid to question the hype, to dig deeper into the claims being made about AI. The more we understand about how these systems work, the better prepared we'll be to navigate the AI-powered world of the future.
And who knows, maybe you'll be the one to come up with that revolutionary new architecture. The world of AI is full of possibilities, and it's waiting for people like you to explore them.
So keep that curiosity burning, keep asking those tough questions.
And never stop learning.